Hi guys, welcome to A Simplified Education. In the last lecture we have discussed the first law of thermodynamics in detail. Now we will discuss the application of first law of thermodynamics, that is steady flow processes. And before coming to the steady flow process, I just want to introduce with the flow work process. So what is the flow work? It is the work transfer involved to entering or leaving a fluid element by the control volume. Suppose this is our entry point of this control volume system and this is our exit point of this control volume system. So the work transfer involved for the fluid to enter or for the fluid to leave this control volume is named as flow work. So for the control volume, it has to be an open system. We know that for closed system there is no mass transfer, but it is an energy transfer. So for closed system it is named as control mass system, but open system is named as control volume system. So work done by passage 1 to entry mass inside the control volume will be this P1 is pressed at inlet, this P2 is pressed at exit. So if I will write TW equal to PA into dx, okay, and A dx is nothing but volume, this is in volume, so P into dV. So if I will integrate up to 0 to V1 at inlet, so it will be P1 V1, that will be W. So whenever someone will ask you what is the flow work, the one thing you should tell, that is PV. Flow work means pressure into volume, PV, this much at inlet, at exit, at any point, at inlet or at exit, both the times. At inlet it will be P1 V1, at exit it will be P2 V2. So the flow work means PV. That's it, simple. Next, coming to the steady flow energy equation. So what is steady flow, what is unsteady flow? Steady flow means if the flow remains constant with respect to time, we call it as steady flow. If the flow varies with respect to time, we call it as unsteady flow. So for steady flow, if I take this is in control volume, at inlet mass is m1, pressure P1, volume V1, velocity also small v1, h1 is the enthalpy, specific enthalpy, u1 is the specific internal energy, and z1 is the potential energy it is having from the datum. Similarly for the point 2, this is the control volume and work is done by the system is W control volume, and work heat is supplied to the system is Q. So this is in system. I am now going to observe this system for steady flow. So for conservation of mass, this m1 and m2 will be equal to m, because whatever the mass it is entering at the inlet, it has to leave from the exit point. So for the conservation of mass, m1 will be m2 will be m. And for conservation of energy, the total energy at inlet will be equal to total energy at exit. That's why E at inlet will be equal to E at exit. So energy at the inlet is equal to the energy at exit. So energy at inlet is consist of internal energy, kinetic energy, potential energy, and heat energy, which is given as the input to the control volume. And at the exit we are getting internal energy, kinetic energy, potential energy, and work is the output that we get from this system. Work is the output from the control volume. But this net work involves, at inlet the flow work has to be given, at outlet the flow work has to be taken from the system, and control volume work done which we get from the system. So this is the net work done. If we substitute in place of W net this expression, then we will get E1 plus V1 square by 2 plus GZ1, and I have divided the mass in each expression over here, Q by m. and u2 plus v2 square by 2 plus dz2, and I have replaced in place of w net the expression over here, and I am taking p1 v1 to this side, p2 v2 not p2 v2 as it is having the positions. So p1 v1 coming to this side, u1 plus p1 v1 making h1 v1 square by 2 gz1 q dot by m representing small q, s2 likewise u2 plus p2 v2 is h2 v2 square by 2 and gz2 w cv by m. Okay, so this is the final expression that we are getting, h1 plus v1 square by 2 plus gz1 plus small q equal to h2 plus v2 square by 2 plus gz2 plus control volume work done. This is our steady flow energy equation, the final expression. Next, coming to the examples of steady flow, a steady flow is the application of fast flow. What are those devices, mechanical devices that we apply the steady flow energy equations? One is nozzle, compressor, diffuser, heat exchanger, turbine, throttling devices. We will discuss one by one. So the assumptions made for these mechanical devices for the steady flow energy analysis are perfectly insulated chamber, change in potential energy and kinetic energy are neglected, no work transfer, and finally steady flow. Steady flow means the properties does not vary with respect to time. So coming to nozzle, as this is a nozzle, the velocity at the inlet is lesser than the velocity at the outlet. So according to the steady flow energy equation, we know this expression is no work transfer, no heat transfer is there. I am making this to as 0, and also there is no potential energy considered in case of a nozzle. Now I get the expression h1 plus v1 square by 2 equal to h2 plus v2 square by 2, but I told you that the energy at the outlet, that is v2, is much greater than v1. So v1 is also 0. So the final expression I am getting is v2 equal to 2 into h1 minus h2. So whenever you are solving a steady flow energy equation problem, first focus on the data that is given in the question, then you write down this equation, this main equation. Okay, after writing down this main equation, whatever data is given in the question, you take the data and you put the data in this equation, and whatever the data it is not given in the question, you make those data as 0, then you solve the question, you will definitely get the answer. Okay. Next, coming to the diffuser, diffuser behaves exactly opposite to the nozzle. Okay, so if I have told the potential energy is 0, this is 0, work transfer is also 0, the velocity at this point is higher than the velocity at this point, so v2 will be 0. So I can write v1 equal to 2 root over of h2 minus h1. Okay, this is in case of diffuser. Next, coming to the turbine. So for turbine, this energy is 0, q is also 0 as it is not taking any heat input now, so we assume that q is 0, gz2 is also 0, turbine produces work. Okay, so we will only focus on work as there is no velocity or no kinetic energy also neglected, so we can get control volume is h1 minus h2 and it will be positive, the control volume work done, because h1 is greater than h2. But when you are solving a question for steady flow energy equation, first you have to write the main equation, whatever the data it is given in the question, you put those data in the equation. After that, the data that has been not given in the question, the data which is not present in the question, you make that data as 0, then you proceed with your answer, you will definitely reach the solution. Okay. Next, coming to the compressor, for a compressor it is opposite to the turbine, so the answer we will get is W control volume will be H1 minus H2, other thing will be 0. potential energy, kinetic energy, heat energy. Okay, other thing we will get is 0, and control volume work done will be negative as H2 is greater than H1. Okay, next coming to the heat exchanger. For heat exchanger, it takes some heat. This is 0, this is 0, this is 0, this is 0, this is 0. So the Q will be H2 minus H1. Next coming to the final device, final mechanical device, that is throttling device. So throttling device means if the flow is occurring through a very small opening, or flow through a capillary action, or flow through porous plug, or flow through partially open valve. So all these flow through very small opening, flow through partially open valve, all these contributes to the throttling devices. The main characteristics of throttling process is no heat transfer, no work transfer, change in potential kinetic energy are neglected. It will be an isenthalpic process, and it's also an irreversible process. This is P1, and the pressure P2 is over here, and P2 is greater than P1. The pressure present over here will be higher, then only the fluid present here will move to in upward directions. So I have already told you the heat transfer and work transfer are 0. So from the steady flow energy equation we know this value, right? So from the steady flow energy equation we know this value. As the kinetic energy and potential energy are neglected, I am making it 0, no heat transfer, no work transfer. So H1 will be equal to H2, that means enthalpy R remains same. So it is named as isenthalpic process. It is named as isenthalpic process. In case of throttling means H1 equal to H2. You should understand this. Next, coming to the unsteady flow energy equations. I am now completing the steady flow. Now coming to unsteady flow energy equation. If the flow varies with respect to time, we call it as unsteady flow. If the flow does not vary, we are telling it steady flow. But if the flow varies with respect to time, then we call it as unsteady flow. That means flow behavior changes means there should be accumulation of mass and energy in the control volume. Whatever mass is entering, the mass exiting is not same. According to the conservation of mass, mass entering is not equal to the mass exiting. That means some amount of mass and energy are accumulated in the system. Also, according to the conservation of energy, also energy at inlet is not equal to energy at exit, right? So from that you can say this is a control volume same as the steady flow process, but the thing is mass at inlet and exit are not same, energy at inlet and exit are not same. Now coming to the conservation of mass, we know this dm by dt at control volume, change in mass will be m dot I minus m dot E, energy at inlet minus mass at inlet minus mass at exit. And conservation of energy, if I write change in energy equal to energy at inlet minus energy at exit. So change in energy, energy at inlet will be enthalpy, kinetic energy, potential energy, heat energy. Energy at exit will be enthalpy, kinetic energy, potential energy, work energy. But change in PE and KE are neglected. Potential energy and kinetic energy are neglected. So this term and this term will be 0. This term and this term will be also 0. Now delta E will be MIHI plus Q minus MEHE minus W. Differentiating both sides with respect to time, you will get d by dt equal to d by dt of MIHI, which will be represented at m dot I, d by dt of Q, d by dt of MEHE minus d by dt of W. And the final unsteady flow energy equation, you will get that d by dt of control volume equal to m dot I HI plus Q dot minus m dot EHE minus W dot. Dot means divided by time. Okay, so this is our unsteady flow energy equation, the final expression. Next coming to a question which is actually named as charging of tank. but I am representing it through a question. The insulated pressure cylinder of volume V contains air at a pressure P1 and a temperature T1. It is to be filled from a supply pipeline maintained at a pressure Pi and temperature Ti, so that the final temperature of air in the cylinder after it has been changed to pressure same as supply line. This is the expression. You have to prove that the final temperature of this pressure cylinder is this much. So, this is in pipeline where the fluid is flowing or the air is flowing, and this is an insulated chamber. When the pipeline the air is flowing, it is coming to this chamber. Okay, we are asked to calculate the final temperature of this chamber, and the energy mass at the exit is 0 because it is an insulated closed chamber. No mass is going out, right? So, for this chamber we have to calculate the temperature. So, according to the unsteady flow equation, we know that du by dt of control volume equal to m dot I hi plus q dot minus m dot e he minus w dot. As there is no heat transfer into the insulated chamber, q dot will be 0, nothing is coming out, that means this will also 0. There is no work transfer also, that's why W term will be 0. So, du by dt of control volume will be equal to m dot I into hi. M dot I hi means dm by dt into hi. Dt cancelled both sides, du of control volume equal to dm into hi. Okay. Now, if I will write this, du of control volume as Cv into m2 into T2 minus m1 into T1, that is equal to m2 minus m1 ui plus pi vi. What is m2 and m1? This is very important. M1 is initially, as it is an unsteady flow process, initially some mass is present in the insulated chamber. Okay, M2 is finally present mass. Initially some mass is present and M2 is finally some mass is present. Mi is the amount of mass entering into the chamber, insulated chamber. Okay, so I can write here, if I multiply Cv everywhere, then I will get Pi V divided by RT2 into CVT2 minus P1 V1 divided by RT1 into Cv into T1, that is equal to Pi V divided by RT2 minus P1 V divided by RT1 whole into Cp into Ti. If you write, expand this M2 into this form, M1 in this form, M2 is the final mass which is going to be present over there, but for P2 is equal to Pi, that's why I have directly written, in place of P2 I have directly written Pi. Likewise, if you expand this, you will get this. After that, if I again rearranging this, Pi minus P1 equal to Pi by T2 minus P1 by T1 into gamma into Ti. If you rearrange this equation, you will finally get the expression of T2 as gamma Ti divided by 1 plus P1 by Pi whole into gamma Ti divided by T1 minus 1. Okay. So, this is the end of the steady flow and unsteady flow energy equation. Okay. In the next lecture we will start with the second law of thermodynamics, which is the introduction to the entropy. So thank you.